The mystery of electric charge and its fundamental role in the universe. When we begin to ask the most fundamental questions about the universe, we quickly find ourselves at the doorstep of electric charge. What exactly is it that makes one particle repel another, or that draws two particles together with an invisible yet undeniable force? Why is it that this property, which cannot be seen, smelled, or tasted, defines so much of the structure of reality? Electric charge is one of the most basic characteristics of matter, a property as intrinsic as mass, yet far more mysterious in how it behaves. To call it a mystery is not to suggest that we are entirely ignorant of its workings. We understand the mathematics that describe how charges interact, how opposites attract and likes repel, and how the strength of their attraction diminishes with distance. We know how to measure it, how to use it, how to control it in our technologies. But to answer the question of what charge truly is, or why the universe contains it, in the first place, pushes us into territory where science meets philosophy. Imagine a universe with no electric charge. Atoms could not exist, because electrons would have no reason to orbit nuclei, nor would nuclei themselves remain stable. Matter would dissolve into a soup of indistinguishable particles that never bind, never coalesce, never produce chemistry. Stars would not ignite, planets would not form, and life could never emerge. In this sense, charge is not just a curiosity, it is the scaffolding of existence. To understand charge is to understand why the universe has structure at all. The particles we call electrons, protons, and neutrons are the carriers of this property, and they determine the rules by which all matter interacts. But before science identified them, humans had long been aware of the strange and powerful behavior of charged objects. The earliest recorded encounters with electric charge go back thousands of years. But the day you said enough is enough, when rubbed with fur, that's the day everything changed. The Greek word for amber, electron, gave us the term electricity. For centuries, this was viewed as an odd trick of nature, an amusing curiosity rather than a key to the cosmos. But even in this primitive observation lay the seed of something profound. Somehow, rubbing amber transferred a property that was invisible but detectable, a property that allowed it to reach out across empty space and exert influence. That, in essence, is the mystery of charge, the ability of one object to affect another without contact, to create force where there is nothing visible in between. As human understanding developed, experimenters of the 17th and 18th centuries, such as William Gilbert, Benjamin Franklin, and Charles Augustin de Coulomb, expanded the study of these strange effects. They discovered that there were not just one but two types of charge. Franklin gave them the names positive and negative, although the choice of which was arbitrary. What mattered was that they were opposites, and that the interaction between them obeyed a law of attraction and repulsion. Coulomb, with his precise torsion balance experiments in the late 1700s, was able to establish quantitatively how charges interact. He showed that the force between charges is proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. This became known as Coulomb's law, the electric counterpart to Newton's law of gravitation. Unlike gravity, which only attracts, charge could both attract and repel, introducing a symmetry that made it even more versatile in shaping the universe. To appreciate the role of electric charge, one must consider the scale at which it operates. At the level of atoms and molecules, charge governs everything. It determines how electrons bind to nuclei, how atoms share or exchange electrons to form molecules, how chemical bonds hold together the structures of DNA, proteins, and countless other molecules essential to life. It is the reason that water molecules are polar, giving rise to surface tension, solubility, and the very possibility of biology. At the macroscopic scale, charge is less obvious because most objects are electrically neutral, their positive and negative charges balanced. But even here, charge manifests in lightning bolts that tear across the sky, in the circuitry of every electronic device, and in the magnetic fields generated by moving charges that protect our planet from cosmic radiation. Without charge, not only would atoms not exist, but the universe itself would lack the complexity that allows for galaxies, stars, and life. Yet what is charge itself? It is not something that can be broken down into simpler components. We cannot say an electron is negative because it contains smaller negative pieces. As far as we know, charge is fundamental, a basic property of certain particles that simply is. In physics, we call such properties intrinsic. Mass is intrinsic, spin is intrinsic, charge is intrinsic. Just as mass gives rise to the gravitational force, charge gives rise to the electromagnetic force. These are not optional add-ons to particles, they are the defining characteristics that make the particles what they are. An electron without negative charge would not be an electron at all. It would be some entirely different entity. Modern physics frames charge within the elegant structure of field theory. Every particle that carries charge is coupled to a corresponding field, the electromagnetic field. When we say that two charges exert a force on each other, we are describing the way they interact through this field. The field permeates all of space, and charged particles are disturbances or excitations within it. The photon, the quantum particle of light, is the messenger of this interaction, the carrier of the electromagnetic force. When two electrons repel each other, what is happening at the quantum level is an exchange of virtual photons, a constant dialogue of force that never ceases. This perspective, born out of quantum electrodynamics, gives us the most precise and accurate description of reality ever constructed. Yet even within this framework, the question of why charge exists, or why it comes in exactly the values that it does, remains unanswered. One of the most remarkable facts about electric charge is its quantization. All observed charges are multiples of a fundamental unit, the charge of the electron. Protons carry exactly the opposite charge, positive and equal in magnitude, while neutrons carry none. Quarks, the constituents of protons and neutrons, carry fractional charges, either 2/3 or 1/3 of the electron's charge, but these never exist in isolation. Instead, they combine to form whole charges, ensuring that the observable world always deals in exact, balanced quantities. This quantization is crucial. If charges varied continuously, matter could not form stable, repeatable structures. The predictability of chemistry, the order of the periodic table, and the reliability of physical laws all depend on the discreteness of charge. There is another aspect to charge that deepens the mystery: conservation. Charge cannot be created or destroyed. It can only be transferred. In any closed system, the total amount of electric charge remains constant. This principle, charge conservation, is one of the most fundamental symmetries of the universe. When electrons flow through a wire, they may leave one place and arrive at another, but the net charge is unchanged. When particles collide and transform into new particles, the sum of charges before and after must be the same. This symmetry is not just an observation. It is a mathematical consequence of the laws of physics. In the language of modern theoretical physics, charge conservation arises from gauge symmetry, a principle so deep that it underpins not only electromagnetism, but also the other fundamental forces of nature. To grasp the significance of this, consider how fragile the universe would be if charge were not conserved. Particles could spontaneously appear with unbalanced charge, destabilizing atoms and molecules, producing runaway fields that would shred any attempt at structure. The stability of matter and the very predictability of physical law are guaranteed by the fact that charge is eternal and unchanging. It is not only a property, but also a principle, a constant thread running through the tapestry of the cosmos. From a cosmic perspective, charge plays another crucial role. It allows the universe to remain electrically neutral on the largest scales. Despite the countless trillions of electrons and protons scattered throughout the cosmos, their charges balance almost perfectly. This balance is not an accident, but a necessity. If the universe had even a tiny imbalance of charge, the resulting electric forces would overwhelm gravity, tearing apart galaxies and preventing stars from forming. The fact that the universe is nearly neutral suggests that nature has built-in mechanisms to ensure this balance, though the deeper reasons remain one of physics' open questions. And yet, in all this wonder, there is an irony. The labels positive and negative are purely human inventions, arbitrary choices made centuries ago. Benjamin Franklin could just as easily have reversed them, and then today we would say that electrons are positive and protons negative. The universe itself does not care about the names. It only cares about the relationships. Opposites attract, likes repel, balance is maintained. The labels are ours, but the phenomenon is real. Charge is not just a property of particles, not just a number in an equation, but a principle that shapes the universe at every level. It is the reason atoms exist, the reason chemistry works, the reason stars shine, and the reason life has form. And yet, even with all our knowledge, its ultimate origin remains elusive. Why does an electron have the charge it does? Why does the proton's charge so perfectly balance it? Why is charge quantized rather than continuous? These are questions that push us to the edge of our understanding, into the realm where physics becomes philosophy. This is the beginning of the story of electric charge, the mystery of why it exists at all, and the recognition that it plays a fundamental role in the universe. In Part B, the exploration will continue into deeper layers of the mystery, how charge relates to symmetry, why its exact values matter, and how its existence connects to the grand structure of physical law. To appreciate the true depth of electric charge, one must recognize that it is not only a property of individual particles, but also a reflection of nature's insistence on balance and symmetry. Physicists often say that the laws of the universe are written in the language of symmetry, and charge is one of the clearest examples. The electron and the proton are not merely particles with opposite signs. They are mirror partners in a cosmic equation. Their charges are not almost equal or close enough. They are exactly equal in magnitude to as many decimal places as science can measure. This uncanny precision raises questions far beyond chemistry and physics. It touches on the very reason the universe exists at all. Consider what would happen if the electron and proton did not perfectly balance each other. Imagine if the electron's charge were just a tiny fraction stronger than the proton's. Then every atom would carry a slight excess of negative charge. That excess, multiplied by the countless atoms in stars, planets, and living things, would generate repulsive forces so powerful that matter could never assemble into stable forms. Conversely, if protons were slightly stronger, then all matter would collapse under the unbalanced attraction of positive charge. In either case, the universe would not exist in any recognizable form. The fact that the electron and proton are perfectly matched is one of those delicate cosmic balances that appear finely tuned for the existence of structure, complexity, and life. In theoretical physics, this balance is framed in terms of symmetry principles called gauge symmetries. A gauge symmetry is a rule that says you can change certain aspects of a system, like the overall phase of a wave, function without altering the physical reality. The conservation of electric charge, which we observe everywhere in the universe, emerges naturally from such a symmetry. This connection, established by Emmy Noether in the early 20th century, is one of the most profound insights in modern physics. Noether's theorem links symmetries to conservation laws. If a system has a continuous symmetry, there must be a conserved quantity. In the case of electromagnetism, the symmetry of the equations under certain transformations guarantees the conservation of charge. Thus, what might seem like an arbitrary rule of nature, that charge cannot be created or destroyed, is in fact a logical consequence of a deeper symmetry. Charge, then, is not simply there. It is tied to the geometry of the universe itself. The way particles interact, the way fields stretch across space, the way light and matter weave together, all of it is grounded in the symmetry that gives rise to charge. And this realization forces us to ask, could it have been otherwise? Could there be a universe in which particles exist without charge, in which only mass and gravity determine structure? Perhaps, but such a universe would be lifeless and uniform, with no chemistry, no light, no energy exchange. It would be a silent cosmos, devoid of the richness we associate with existence. The mystery deepens when we consider antimatter. For every electron, nature allows the existence of a counterpart, the positron, identical in every way except that its charge is positive. When an electron and a positron meet, they annihilate each other, releasing energy in the form of photons. This pairing suggests that charge is not just about attraction and repulsion, but about the very structure of the universe's duality. Matter and antimatter are woven together, and charge is the marker that distinguishes them. Yet the universe we observe is overwhelmingly dominated by matter, not antimatter. Why did the balance tip in favor of electrons and protons rather than their opposites? This question, known as the mystery of baryon asymmetry, is one of the deepest puzzles in cosmology. If equal amounts of matter and antimatter had been created in the Big Bang, they would have annihilated one another, leaving behind nothing but radiation. Instead, some tiny asymmetry allowed matter to survive. That asymmetry, expressed in the charges of particles, is the reason galaxies, planets, and people exist. When we look closely at how charge shapes interactions, another striking feature emerges: its range. The electromagnetic force, which charge creates, is effectively infinite in range, though it diminishes with distance according to Coulomb's law. This is in sharp contrast to the strong nuclear force, which binds quarks inside protons and neutrons, but only at subatomic scales, or the weak nuclear force, which operates at even shorter ranges. Because it is long range, electromagnetism is responsible for the large-scale dynamics of plasma in stars, the formation of magnetic fields around planets, and the behavior of interstellar gas clouds that eventually collapse to form stars. Gravity dominates on the largest cosmic scales because it always attracts and never cancels. But at the level of atoms, molecules, and life, electromagnetism is the architect. The way a flower blooms, the way a bird flies, the way neurons fire in the brain, all of these are electromagnetic phenomena, made possible by the property of charge. And yet, for all its power, charge is invisible. We cannot see it directly. We can only see its effects. This invisibility has always given it an aura of mystery, from the days when Franklin played with lightning to the present experiments in particle accelerators. What we call electricity is simply the movement of charges, yet this simple movement drives the entire technological infrastructure of our world. Every light bulb, every computer, every smartphone, every medical device depends on the manipulation of charges. Humanity has learned to harness charge without ever fully understanding why it exists in the form it does. It is as though we have mastered the use of fire without knowing its source. Some of the most advanced theories in modern physics attempt to peer beneath the surface of charge. In the framework of the Standard Model, charge is not a random label, but a consequence of how particles interact with underlying fields. Quarks, leptons, and gauge bosons all carry charges that determine how they couple to these fields. The electromagnetic charge is just one example of a broader concept called gauge charges. In the electroweak theory, which unifies electromagnetism with the weak force, electric charge arises as a combination of more fundamental properties, weak isospin and hypercharge. This unification reveals that charge is not arbitrary, but emerges naturally from deeper structures. Still, it leaves unanswered the ultimate why. Why do particles have the specific charges they do? Why is the electron's charge what it is, rather than twice as large or half as small? These are constants of nature, numbers that must simply be measured because theory does not yet explain them. In particle physics, even a tiny change in the value of the electron's charge would rewrite the universe. If the electron carried more charge, its attraction to protons would be stronger, shrinking atomic orbitals and altering chemistry beyond recognition. If it carried less, atoms would be too loosely bound to form stable molecules. Life as we know it depends on the precise value of this property, suggesting that charge is part of the fine-tuning of the universe. Some scientists see in this fine-tuning evidence of deeper principles yet undiscovered, while others invoke the idea of a multiverse, in which many possible universes exist, each with different values for fundamental constants, and we happen to live in one where charge permits life. The human story of charge is also one of wonder and humility. We began with amber and fur, moved through sparks and lightning, built machines that harnessed the flow of charges, and now probe the quantum fields that give rise to them. Yet at every stage, the mystery has deepened. The more we know about charge, the more profound the questions become. Why does charge come in exactly two polarities, positive and negative, and not three or more? Why is it that like charges repel and unlike charges attract, why not the reverse? These questions may sound naive, but in science, naive questions often lead to revolutionary answers. What makes charge so fascinating is that it is both utterly familiar and fundamentally strange. We encounter it every day when we flip a switch, yet at the heart of it lies a puzzle that has no final solution. To say that electrons are negative, protons positive, and neutrons neutral is to state a fact, but not to explain its origin. The labels themselves are human choices, but the reality they represent is deeper than human language. Charge is not just a property. It is the silent architect of the universe, the invisible sculptor that shapes every atom and molecule. It is the law that enforces balance, the symmetry that maintains order, the thread that ties the smallest particle to the largest galaxy. The mystery of electric charge, then, is not one that science can easily resolve with a single equation or experiment. It is a mystery that invites us to keep probing, to keep asking, to keep refining our understanding of nature. Perhaps one day, new physics beyond the standard model will explain why charges have the values they do, why they come in pairs of positive and negative, why they balance so precisely. Until then, we stand in awe of a property so simple to describe and yet so essential that without it, there would be no stars, no planets, no life, and no one to ask the question. Charge, in the end, is the universe's way of ensuring that interaction, structure, and life are possible. It is the invisible handwriting of nature, inscribed into every atom, guiding the dance of matter and energy. And though we may call it a mystery, it is a mystery that sustains us, a reminder that even the most familiar aspects of our world are rooted in profound secrets waiting to be uncovered. How electrons came to be defined as negative and protons as positive, the story of why electrons are called negative and protons positive, is not one of deep physical necessity, but of history, convention, and a little bit of accident. To ask why an electron carries negative charge and not positive is to misunderstand the nature of scientific naming. The choice could easily have been reversed, and the universe would be no different. The forces, the balance, the chemistry, all would remain unchanged. But the path of history is often shaped by arbitrary decisions that, once made, become fixed in the language of science forever. The mystery of charge polarity is therefore not a mystery of nature itself, but of the way humans came to describe it, and of how that description has influenced our perception of the universe. Long before electrons and protons were known, before the word atom had any real scientific meaning, humans encountered electricity in its raw, natural form. Lightning streaked across the sky with terrifying power. Sparks leapt from rubbed amber, crackling into the air. Strange forces seemed to allow certain materials to attract or repel each other without touching. These were the earliest hints of a hidden property of matter, invisible yet undeniable. Ancient Greek philosophers noted that amber rubbed with fur could pull light objects toward it, and they gave this strange phenomenon its first name, electron. For centuries afterward, such curiosities remained little more than parlor tricks, entertaining but not understood. It was not until the 17th and 18th centuries that systematic experiments began to reveal patterns. William Gilbert, physician to Queen Elizabeth I, studied the properties of magnets and electrified materials, distinguishing between the two. He recognized electricity as something different from magnetism, even though both involved unseen forces. Then came Otto von Guericke, who built one of the first electrostatic machines in the 1600s, creating sparks by rubbing sulfur globes. Each discovery built toward a realization that there were not one but two distinct kinds of electricity. Benjamin Franklin, experimenting in the mid-1700s, was one of the first to suggest a simple way of thinking about this duality. He imagined electricity as a kind of fluid that could flow from one object to another. If an object had too much of this fluid, it was positively charged. If it had too little, it was negatively charged. Franklin's model was crude, but his naming stuck. He arbitrarily assigned the glass rod rubbed with silk as positive, and the rubber rod rubbed with fur as negative. There was nothing in nature that demanded this choice. He could have swapped the names, and the world would function identically. But Franklin's convention endured, becoming the foundation of the vocabulary of electricity. It is here that history made its quiet decision. When, more than a century later, scientists discovered the electron, they had to fit it into Franklin's framework. J. Thomson, in 1897, identified the electron as a particle with a measurable charge. He observed its behavior in cathode ray tubes, watching the beam of particles bend under electric and magnetic fields. The direction of the deflection revealed that these particles carried the kind of charge Franklin had called negative. Thus, the electron was christened the bearer of negative charge. A century-old choice of terminology, made without knowledge of electrons, had suddenly become etched into the foundation of physics. The proton's name followed naturally. Ernest Rutherford's experiments in the early 20th century showed that atoms contained dense, massive cores. Within those cores were particles whose charges exactly counterbalanced those of electrons. Since the electron was already labeled negative, its counterpart had to be labeled positive. The symmetry was perfect, the language consistent, but again, it was a convention. If Franklin had made the opposite choice, we would today speak of protons being negative and electrons being positive. Physics would remain unchanged, only the labels would be reversed. It is fascinating to reflect on how much weight language carries in shaping our view of the world. By calling electrons negative, we unconsciously associate them with ideas of minus, deficiency, and lack. Positivity, by contrast, carries connotations of abundance, affirmation, and stability. These cultural associations can sometimes color how we think about science, even though nature itself is indifferent to human meanings. In truth, electrons are no less positive in their importance than protons. They are vital for chemistry, electricity, and life itself. The label negative is nothing more than a historical accident, but one that has persisted for centuries. The deeper question is whether nature itself distinguishes between positive and negative in any absolute way. The answer seems to be no. What matters is the relationship. Opposite charges attract, like charges repel. The universe does not care which one we call positive or negative. It only enforces the rule that they are opposite. When an electron meets a proton, their charges cancel, producing a neutral atom. If we had chosen the opposite labels, the result would be identical. What is fundamental is the balance, not the sign. Still, the choice of sign has consequences for how physics developed, particularly in the equations that describe electric and magnetic fields. Coulomb's law, Maxwell's equations, and later quantum electrodynamics all make use of positive and negative charges in their formulations. The mathematics works regardless of sign convention, but the consistency of notation is crucial. Every textbook, every experiment, every circuit diagram relies on the shared understanding that electrons are negative. In this sense, Franklin's arbitrary decision centuries ago became one of the most enduring standards in science, shaping education and communication worldwide. There is also a subtle irony in the history of electrical science. For much of the 18th and 19th centuries, scientists believed that electric current flowed from positive to negative, in line with Franklin's fluid model. They assumed the flow of electricity in a wire was a movement of positive charges. Only later, when the electron was discovered, did it become clear that in most conductors, it is the negatively charged electrons that move, not the positive charges. By that time, however, the convention of current flowing from positive to negative was so entrenched that it was never changed. To this day, engineers speak of conventional current flowing in the opposite direction of the actual electrons. It is a relic of history, a quirk of naming that survives in the very heart of modern technology. As science advanced into the 20th century, The question of why particles carry the charges they do became central to particle physics. Quarks, discovered in the 1960s, carry charges of +2/3 or 1/3 in units of the electron's charge. These combine to form protons with a total charge of +1 and neutrons with no net charge. The electron's charge, by definition, is 1. Again, the minus sign is not a fundamental truth of the universe, but a matter of convention. What is fundamental is that charges are quantized, always appearing in exact multiples of this elementary unit. The mathematics of the Standard Model encodes these charges as intrinsic properties, but it does not dictate whether we should label them positive or negative. And yet, even if the labels are arbitrary, the symmetry they represent is anything but. The balance of opposite charges is one of the deepest principles of the universe. Without it, matter could not form. Without it, the cosmos would be dominated by overwhelming electric fields that would tear it apart. In this sense, the story of why electrons are negative and protons positive is both trivial and profound. Trivial, because the labels could have been reversed. Profound, because the existence of opposite charges at all is the very reason matter exists. The journey from Franklin's glass rods to Thomson's cathode rays and Rutherford's gold foil experiment illustrates how scientific language evolves. It is built from human choices, sometimes arbitrary, sometimes inspired, always rooted in the context of the times. Those choices can become permanent, not because nature demands them, but because human society adopts them and carries them forward. The negativity of the electron is one such choice, and its permanence has shaped how generations of students and scientists understand the atomic world. How electrons came to be defined as negative and protons as positive, the decision to call electrons negative and protons positive may seem trivial, but when we look more closely, we discover that it shaped the very language of science, the way electrical theory developed, and even how engineers, educators, and philosophers framed their understanding of nature. It is a story that reminds us how profoundly human choices interact with universal truths. Nature supplied the forces, but humanity supplied the names, and those names became the framework through which we interpret reality. One striking example of this is the persistence of the concept of current direction. When Franklin established his convention in the 18th century, he imagined electricity as a kind of fluid flowing from one body to another. He supposed that what we now call a positively charged object had an excess of this fluid, while a negatively charged one had a deficit. Therefore, when electricity flowed in a circuit, he imagined the flow was from positive to negative. This idea became embedded in scientific teaching, and by the 19th century, it was the unquestioned convention for describing electrical currents. But when J. Thomson discovered the electron in 1897, everything changed. The moving charges in a typical wire were not positive, as Franklin had imagined, but negative. Electrons were the carriers of current. Yet by that time, electrical engineering was already flourishing, with textbooks, equations, and designs all written in the language of conventional current, flowing from positive to negative. To revise the convention would have been enormously disruptive. So scientists and engineers chose to keep Franklin's system, even though it meant describing current as flowing in the opposite direction of the actual charges. To this day, students of physics must grapple with this strange historical relic, the fact that the defined current points opposite to the flow of electrons. It is one of the most enduring reminders that scientific conventions, once chosen, are nearly impossible to reverse. The power of naming goes beyond the classroom and the laboratory. Words like positive and negative carry emotional and cultural meanings that can color how we think about the natural world. Positive is associated with good, strong, forward life, giving. Negative, by contrast, suggests deficiency, weakness, even danger. By assigning electrons the label negative, Franklin unknowingly gave them a kind of cultural disadvantage. And yet, electrons are the dynamic, creative agents of the atomic world. They are the reason atoms bond, the reason chemistry exists, the reason electricity flows, the reason life's molecular machinery operates. Without electrons, protons would sit motionless in nuclei, unable to form molecules or drive reactions. In this sense, the negative particle is the true source of activity and variety in the universe. Our naming conceals this fact, subtly biasing our mental image of atomic structure. This interplay between language and science raises deeper philosophical questions. Does it matter what labels we use if the mathematics is the same? Physicists would say no. The sign of charge is arbitrary, a matter of convention. But from a human perspective, the labels shape how generations of thinkers have imagined the atom. Students are told that electrons are negative, protons positive, neutrons neutral, and they accept these as facts rather than conventions. Only later, if ever, do they learn that the choice was arbitrary. By then, the mental framework is already set. In this way, the story of charge polarity illustrates a broader truth, that human perception of the universe is always filtered through the choices of language and history. If we imagine, as a thought experiment, that Franklin had chosen the opposite labels, how different would science look today? In that alternate world, protons would be called negative, electrons positive, and neutrons neutral as always. Current would flow from negative to positive by definition, which would actually match the true movement of electrons in a wire. Students would not have to memorize the strange reversal of conventional current. Engineers would design circuits with electrons moving with the current instead of against it. In that sense, our understanding of electricity might feel more natural, but at the level of physics, nothing would change. The equations of Coulomb, Maxwell, and Schrödinger would look identical, merely with signs flipped. Chemistry would proceed in the same way. Atoms would form the same bonds. Stars would burn in the same brilliance. The universe does not care what names we give its properties. It only cares that those properties exist and follow their rules. And yet, though the labels are arbitrary, the discovery of the actual carriers of charge was anything but. The identification of the electron was a triumph of experimental physics. Thomson's cathode ray experiments revealed a particle far smaller than the atom, with a definite, measurable charge to mass ratio. This was the first concrete evidence that charge resided in discrete carriers, not in some continuous fluid. Later, Robert Millikan's oil drop experiment in 1909 measured the charge of the electron with astonishing precision, showing that it was always the same exact unit, never fractional or variable. This quantization of charge was a revelation. It suggested that nature dealt in indivisible packages of charge, just as it dealt in indivisible packages of matter. The electron became the standard, the definition of what it meant to carry one unit of negative charge. Once the electron was defined as negative, the proton, discovered by Rutherford's team in the early 20th century, became its natural opposite. The proton was massive compared to the electron, about 1008, 136 times heavier, but its charge was exactly equal and opposite. This symmetry is one of the most remarkable facts in physics. The proton's charge arises from the arrangement of its constituent quarks. Two up quarks with charges of +2/3 each, and one down quark with charge 1/3, summing to a total of +1. The electron, meanwhile, is a fundamental particle, indivisible, carrying a charge of 1. That these two charges match so precisely, across particles of such different origin, is a fact that still puzzles physicists. It suggests a deep, underlying principle that unites matter at its most basic level. The neutron, discovered by James Chadwick in 1932, complicated the picture. With no net charge, it seemed an outlier, but even the neutron contains charged quarks, whose values cancel out. Neutrons, in a sense, are hidden carriers of both positive and negative charges, balanced into neutrality. Their existence allowed the atomic nucleus to hold together, preventing protons from flying apart under mutual repulsion. Neutrons are the silent moderators of the atomic world, proof that charge can be present yet concealed. Together, electrons, protons, and neutrons embody the three fundamental states of charge: negative, positive, and neutral. But the naming of those states is human, not natural. The deeper truth is that what matters is not the sign of the charge, but its relative interaction. Opposites attract, likes repel, and balance creates stability. Whether we call them plus and minus, yin and yang, or some other pair of opposites, the relationship is what matters. The universe is built on polarity, and charge is its most basic expression. The story of how electrons came to be defined as negative and protons as positive also speaks to the humility of science. It reminds us that our systems of naming, our frameworks of understanding, are human inventions layered over natural truths. Sometimes those inventions fit perfectly. Other times they are arbitrary but useful. Either way, they carry forward into the culture of science, shaping how knowledge is transmitted across generations. The electron's negativity is a permanent fixture of physics, not because nature demands it, but because history chose it. Yet within this accident of naming lies a profound lesson. Science is not a rigid march toward truth, but a dialogue between human perception and natural reality. We create models, conventions, and labels to make sense of phenomena, and over time those become embedded in the fabric of knowledge. When we look back and see how much was arbitrary, we are reminded of the flexibility and creativity inherent in science. The arbitrary label of negativity attached to the electron did not prevent humanity from unlocking the secrets of electricity, building the modern technological world, and probing the deepest structures of matter. In fact, it shows that science can thrive even when its language is imperfect, so long as its methods are rigorous. In the end, why are electrons negative and protons positive? Because a man named Benjamin Franklin, in a time before atoms and particles were even conceived, needed a vocabulary for two opposing forces. He made a choice, and that choice echoed through centuries of discovery. It shaped the way J. Thomson interpreted his cathode rays, how Millikan reported his oil, drop measurements, how Rutherford explained the nucleus, how textbooks defined current, and how we speak of atoms today. It is a story of contingency, of language, of history, and of the curious way human choices intersect with universal laws. The true marvel is not that electrons are called negative, but that they exist at all, carrying a fundamental property of nature so essential that without them, there would be no matter, no light, no life. Thus, the polarity of charge, as we name it, is both arbitrary and essential. arbitrary in its labels, essential in its reality. The electron's negativity and the proton's positivity are a product of history, but the balance they represent is the foundation of the universe. This paradox of human arbitrariness overlaying cosmic necessity is what makes the story so compelling. It reminds us that while science seeks absolute truths, it does so through the lens of human culture, history, and imagination. And in that blend of accident and necessity lies the beauty of our quest to understand the universe. The deep connection between charge, energy, and stability in atoms. If one wishes to understand the architecture of the universe, it is impossible to escape the trinity of charge, energy, and stability. They are not separate ideas, but interwoven principles that dictate how matter organizes itself. The existence of atoms, the persistence of stars, the complexity of chemistry, and the emergence of life all rest upon this hidden connection. What appears to us as ordinary reality, the solidity of a rock, the flame of a candle, the breath of air in our lungs, is only possible because charges interact with energy to create stability. Without this profound interplay, matter would not cohere, and the cosmos would remain a diffuse cloud of particles adrift in emptiness. At the most basic level, charge defines how particles interact. The electron, carrying its single unit of negative charge, feels an invisible pull toward the positively charged proton. This attraction is not a choice, not a tendency, but a fundamental law of physics. Opposites attract. The electric force binding electron to proton is astonishingly powerful compared to other forces in nature. It is far stronger than gravity, immensely shaping the structure of matter on small scales. If we imagine a hydrogen atom, the simplest atom with one proton and one electron, the electron does not simply fall into the proton and vanish. Instead, energy enters the picture. Quantum mechanics tells us that the electron exists in specific energy levels, orbitals where it can remain bound without collapsing into the nucleus. Here lies the first profound connection. Charge brings particles together, but energy determines the terms of their stability. This interplay between attraction and energy levels ensures that atoms have size, shape, and structure. Without quantum restrictions, electrons would simply spiral into nuclei, radiating energy as they collapsed, and atoms would be no more than point-like singularities. But nature prevents this catastrophe through the quantization of energy. Electrons can only occupy certain discrete states, each with a precise energy value. The lowest of these states is stable, because there is no lower state available for the electron to fall into. In this way, stability is born from the marriage of electric charge and quantized energy. The hydrogen atom, humble though it seems, is the prototype of this principle. Its single proton and electron form a bound system, an island of stability in an otherwise chaotic sea of possibilities. When atoms become more complex, with multiple protons and neutrons in the nucleus and multiple electrons in orbit, the dance between charge and energy grows richer. Protons repel each other with relentless force, each demanding separation from its like-charged neighbors. If nothing counteracted this, the nucleus itself would disintegrate. But the strong nuclear force, operating at subatomic scales, holds the protons together, aided by neutrons that balance the repulsion without contributing additional charge. Once again, stability is not the absence of conflict, but the delicate resolution of competing forces. Charges repel and attract, energy distributes itself across allowed states, and stability emerges as the fragile but enduring equilibrium that defines matter. Consider for a moment the periodic table, that majestic map of elements. Each entry is not just a chemical symbol, but a testament to the balance of charge and energy. As protons increase in the nucleus, electrons must arrange themselves in more complex shells and subshells, each defined by quantum mechanical rules. The distribution of these electrons determines chemical behavior. The difference between reactive sodium and inert neon, between metallic copper and nonmetallic sulfur. At its root, this chemical diversity is simply the manifestation of charges seeking stability, electrons occupying energy levels in such a way that balance is achieved. When an atom reaches a configuration where its electron shells are full, it becomes chemically stable, resistant to further reaction. The noble gases helium, neon, argon stand as examples of this perfect symmetry between charge and energy. Their stability explains why they do not easily bond or corrode or combust. In every case, what looks like chemical personality is really the expression of deep physical principles. But stability is not absolute. It is relative, context, dependent, and dynamic. Sodium, for example, with its single outer electron, is unstable compared to noble gases. That electron is easily lost, and in doing so, sodium reaches a more stable configuration. Chlorine, with 7 electrons in its outer shell, is unstable in the opposite way. It longs for one more electron to complete its shell. When sodium and chlorine encounter one another, their instabilities cancel out. Sodium donates its extra electron, chlorine accepts it, and together they form a stable ionic bond, sodium chloride, common table salt. This act of chemical bonding is nothing more than the rebalancing of charges through the transfer of energy to achieve stability. What we call salt is simply the crystallization of this principle on a macroscopic scale. If we step back from the chemical world and look to the stars, we see the same principle at work on a grand scale. Stars shine because nuclei, bound by strong forces and driven by electric repulsion, undergo fusion. Protons, normally kept apart by their positive charges, are forced together under immense pressure and temperature, overcoming their repulsion long enough for the strong nuclear force to bind them into helium nuclei. In this process, a portion of their mass is converted into energy, released as the light and heat that sustain planets and life. Here again, charge, energy, and stability are entwined. The stability of stars arises not from stasis, but from a dynamic balance. Gravitational collapse pulls matter inward, nuclear fusion pushes energy outward, and between them lies a stable star. For billions of years, this equilibrium holds, all because the laws of charge and energy dictate how protons can fuse and how atoms can endure. The concept of stability also extends into the nucleus itself, where charge and energy engage in a subtler dance. Certain nuclei are stable indefinitely, while others decay over time, releasing radiation. Why? The answer lies in the balance of protons and neutrons. Too many protons create excessive repulsion, destabilizing the nucleus. Too many neutrons create imbalance, leading to decay. Only certain combinations yield stability, and those combinations are reflected in the chart of nuclides, a nuclear periodic table. Uranium, with its heavy, unstable nucleus, undergoes fission, splitting into smaller, more stable nuclei and releasing vast amounts of energy. The very possibility of nuclear power and nuclear weapons rests upon this principle. That stability in the nucleus is a delicate equilibrium of charge and energy, and when disrupted, the result is a dramatic release of stored potential. Even at the smallest scales, this connection reveals itself in surprising ways. In quantum electrodynamics, the most precise theory in physics, the behavior of charged particles and their interactions with energy fields are described with astonishing accuracy. The equations predict how electrons exchange photons, the carriers of the electromagnetic force, and how these exchanges determine everything from the structure of atoms to the scattering of particles in accelerators. In these equations, charge is not just a property, but a source of interaction. Energy is not just a quantity, but the currency of stability. The fact that this theory has been tested to 1 part in a trillion and found correct underscores the depth of the connection. It is not metaphorical but exact, written into the mathematical fabric of reality. Yet, for all our understanding, mysteries remain. Why, for example, are the charges of the electron and proton equal in magnitude? This symmetry is essential. If they differed even slightly, atoms would not be neutral, and the universe would be electrically unstable. But physics offers no simple answer. It is a fact we observe, a law we measure, but not one we fully explain. Similarly, why do quantized energy levels exist? Why is stability achieved in discrete steps rather than continuous gradients? Quantum mechanics provides the framework, but the deeper why remains elusive. These mysteries remind us that the connection between charge, energy, and stability, though deeply understood in practice, still points to profound truths beyond our grasp. The everyday world is filled with manifestations of this principle, often unnoticed. The reason metals conduct electricity is that their outer electrons are loosely bound, able to move freely in response to electric fields. The reason insulators block electricity is that their electrons are tightly bound in stable configurations, unwilling to shift. The reason molecules form specific shapes is that electrons arrange themselves to minimize energy while balancing the repulsions of like charges. The reason life depends on ATP molecules in cells is that they store energy in chemical bonds whose stability can be finely controlled and released when needed. In every case, the interplay of charges and energy dictates the boundaries of stability, shaping not just atoms but the flow of life itself. Seen from this perspective, stability is not an accident but the natural outcome of a universe governed by charge and energy. Matter is not static but a restless balance of forces, held in place by invisible rules. To ask why atoms are stable is to ask why charges and energies exist in such a harmonious relationship. And though we may never fully answer that question, we can marvel at the fact that they do. For without that balance, without that hidden concord between charge, energy, and stability, the universe would be void of structure, void of complexity, void of us. The deeper one explores the relationship between charge, energy, and stability. The more it becomes clear that these 3 elements are not separate threads, but a single woven fabric. What looks to us like distinct phenomena, electricity, magnetism, chemistry, nuclear reactions, are all variations on the same underlying theme. Charge gives matter its polarity, energy gives it motion and potential, and stability emerges from their dynamic equilibrium. Every level of physical reality, from subatomic interactions to galaxies, is governed by this same principle. At the scale of individual atoms, the link between charge and energy determines how electrons arrange themselves around nuclei. The quantization of electron shells is one of the most astonishing revelations of modern physics. Why should electrons not simply occupy any energy they wish? Why are they restricted to discrete levels? The answer lies in the wave-like nature of particles. Electrons are not tiny balls orbiting a nucleus like planets around the Sun. They are quantum waves that must fit into certain standing patterns around the nucleus, like vibrations on a string. Only specific wavelengths, and therefore specific energies, are allowed. This restriction is enforced by the electron's negative charge and its interaction with the positively charged nucleus. The attraction pulls the electron inward, but the wave nature demands discrete states, so the result is a quantized energy spectrum. Stability arises because once the lowest energy level is occupied, the electron cannot simply slide closer without violating quantum rules. The atom becomes a resilient structure, protected from collapse by the combined influence of charge and quantum energy. This principle scales upward into chemistry, where the arrangement of electrons defines how atoms interact. A stable molecule is not merely a collection of atoms glued together. It is a configuration in which electrons have redistributed themselves into new energy states that balance charges across multiple nuclei. Take water, for example. The oxygen atom, with 6 electrons in its outer shell, pulls strongly on electrons. Hydrogen, with just 1 electron, contributes to the bond. When they join, electrons are shared in covalent bonds, lowering the overall energy of the system and creating a stable configuration. The bent shape of the water molecule arises from the repulsion of electron pairs, which arrange themselves to minimize energy while maintaining bonds. This is why water is polar, with partial positive charges on the hydrogens and a partial negative charge on the oxygen. That polarity allows water to dissolve salts, transport nutrients, and serve as the solvent of life. All of this, the stability of the molecule, its structure, its properties, flows from the delicate balance between charges and the energy states they can occupy. Stability in molecules often emerges through energy minimization. Systems naturally evolve toward lower energy configurations, because lower energy means greater stability. This principle governs everything from simple ionic bonds to complex protein folding in living organisms. A protein does not adopt its shape randomly. It folds into the form that minimizes the repulsion of like charges, maximizes favorable attractions, and distributes energy in a balanced way. The entire machinery of life is built upon this hidden drive toward stable, low-energy states. When proteins misfold, when energy balance is disrupted, disease follows. Thus, the fundamental connection between charge, energy, and stability reaches into biology itself, determining not just the structure of matter, but the functioning of life. On a larger scale, the stability of matter itself requires this relationship. The electron's charge is exactly equal and opposite to the proton's, allowing atoms to be electrically neutral. This neutrality is critical. If atoms carried even the slightest net charge, matter would repel itself violently. Imagine if every atom in your body had an excess of even 1 charge in 10 billion. The repulsion would tear you apart. But in reality, nature achieves perfect balance. Every proton's charge is matched by an electron's. Stability at the scale of matter is only possible because charge is quantized and symmetrical, and because energy arranges those charges into balanced structures. The nucleus adds another dimension to this story. Inside the nucleus, protons repel each other fiercely due to their positive charges. The strong nuclear force holds them together, but its range is very short. Neutrons, though neutral, contribute to the strong force without adding repulsion, providing a stabilizing effect. This balance of forces determines whether a nucleus is stable or radioactive. In stable isotopes, charges and energies align in harmony. In unstable isotopes, the imbalance leads to decay, releasing radiation until a more stable configuration is reached. This process is not chaotic but rule-bound, governed by the same interplay of charge and energy that stabilizes atoms. Even the violent release of energy in radioactive decay is, at its heart, the system seeking stability. Nuclear fusion and fission both depend on this principle as well. Fusion, the process that powers stars, forces positively charged protons close enough that the strong force can bind them. Enormous energy is required to overcome their mutual repulsion, but once bound, the resulting nucleus is more stable, and the excess energy is released as light and heat. Fission, by contrast, takes a heavy, unstable nucleus and splits it into smaller, more stable ones, again releasing energy in the process. Both are different manifestations of the same rule. Systems of charge and energy naturally evolve toward stability, releasing energy as they do. It is this principle that lights the stars, drives nuclear reactors, and shapes the periodic table of elements. On cosmic scales, the connection is even more profound. Galaxies, stars, and planets form because gravity pulls matter together. But gravity alone would collapse everything into singularities. What resists collapse is energy, thermal energy in the cores of stars, quantum degeneracy pressure in white dwarfs, neutron degeneracy pressure in neutron stars. Even in these exotic cases, stability emerges from the interplay of charges and energies. Electrons in white dwarfs resist compression because of quantum rules tied to their charge. Neutrons in neutron stars do the same. Black holes represent the ultimate failure of stability, where energy can no longer resist gravitational collapse. Yet even they emit radiation at their edges, as quantum fluctuations of charged particles play out near the event horizon. Everywhere we look, stability is a dynamic equilibrium between forces of attraction, the energy required to resist or balance them, and the charges that give those forces their strength. In daily life, this profound relationship manifests in familiar yet remarkable ways. The stability of metals, the hardness of diamonds, the softness of graphite, the explosiveness of gunpowder, all are consequences of how charges interact with energies. A diamond is hard because its carbon atoms form a rigid lattice where every electron is locked into stable bonds, distributing energy evenly. Graphite, by contrast, has layers where electrons move more freely, creating softness and conductivity. Gunpowder releases energy violently because the bonds between atoms are less stable, easily rearranged into lower energy products with a sudden burst of heat and light. These are not random properties, but predictable outcomes of the interplay between charge, energy, and stability. One of the most beautiful aspects of this principle is its universality. It does not apply only to exotic physics or abstract equations, but to the entire range of existence. The glow of a firefly, the strength of a skyscraper, the rhythm of a heartbeat, the light from a distant star, all are made possible because charge and energy interact to create stability. The laws that govern electrons around protons are the same laws that govern galaxies around black holes. The scales differ, but the principle is eternal, and yet, despite centuries of study, humanity still does not fully grasp the origin of these properties. Why does the electron have exactly its charge and no other? Why does the proton's charge perfectly balance the electrons? Why does the universe seem tuned for stability rather than chaos? These questions touch the deepest mysteries of physics. The Standard Model describes charges and interactions with remarkable precision, but it does not explain why the values are what they are. Theories of grand unification and supersymmetry attempt to provide deeper answers, but so far the ultimate why remains hidden. The universe seems to have chosen values that allow stability, and without them, life could never have emerged. Whether this is coincidence, necessity, or design is a question that extends beyond physics into philosophy and metaphysics. What is undeniable is that stability is not the absence of change, but the balance of forces. An atom does not sit frozen. Its electrons vibrate, spin, and shift within their allowed states. A star does not remain static. It burns, fuses, and evolves over billions of years. A human body does not stay still. Its molecules break down and rebuild endlessly. Stability is the capacity to endure amidst constant change, and it is charge and energy that make this endurance possible. Thus, the deep connection between charge, energy, and stability is not simply a technical fact of physics, but the foundation of reality itself. Without it, the universe would have no atoms, no chemistry, no stars, no planets, no life. With it, we find a cosmos of breathtaking complexity and harmony, where invisible forces create visible worlds. It is a reminder that beneath the surface of everything we see lies a delicate balance, maintained moment by the quiet laws of physics. And in that balance, we find not only the secret of atoms, but the secret of existence. Why neutrons carry no charge and their hidden role in the atomic nucleus in the heart of every atom lies a mystery so subtle that for centuries it escaped the keenest scientific minds. Early models of the atom formed in the wake of J. Thomson's discovery of the electron and Rutherford's revelation of the nucleus painted a picture of positively charged protons bound tightly in the nucleus, balanced by electrons dancing outside. It was a compelling vision, elegant and simple, but it carried a fatal flaw. If protons were the only residents of the nucleus, they would repel one another violently. Each proton, with its unit of positive charge, would push away its neighbors with immense force. The nucleus should, by all logic, fly apart in a fraction of a second. And yet it did not. Atoms were stable, nuclei endured, the world existed. This paradox haunted physics for decades. Rutherford himself, after discovering the nucleus in 1911, suspected that something more resided within. There had to be a force strong enough to overcome the electric repulsion of protons, holding them together in a tiny, dense ball at the center of the atom. At the time, the only known forces were gravity and electromagnetism, and neither could do the job. Gravity was far too weak to bind protons on such small scales, while electromagnetism only created repulsion between like charges. Something new had to exist, a hidden agent of stability inside the nucleus. The mystery deepened when experiments revealed that atomic mass did not add up. Hydrogen had a mass of 1, and helium, with 2 protons and 2 electrons, should have a mass of 4 if protons and electrons were the only particles involved. Yet the numbers did not match perfectly. Extra, unseen mass lurked within the nucleus. It was only in 1932 that James Chadwick, through ingenious experiments with alpha particles and beryllium, revealed the missing piece, the neutron. The neutron was a revelation. It carried mass nearly equal to the protons, but no net electric charge. It was invisible to electrical detectors because it did not interact with electric fields, and that was precisely what made it indispensable. Unlike protons, neutrons could sit within the nucleus without contributing to the electric repulsion. They added binding power without conflict. They served as the glue that allowed nuclei to exist, balancing the fierce repulsion of protons by bolstering the strong nuclear force that held them together. The neutron was the silent stabilizer, the invisible peacemaker of the atomic world. But why does the neutron have no charge? To answer that question, one must dive deeper into the structure of matter. In the mid-20th century, the development of particle physics revealed that protons and neutrons were not elementary after all. They were built from smaller constituents called quarks, bound by the strong force. A proton consists of two up quarks and one down quark, each up quark carrying a charge of +2/3, the down quark carrying 1/3. Add them together, and the result is +1, the charge of the proton. A neutron, by contrast, consists of one up quark and two down quarks, +2/3 from the up quark, 1/3 from each of the two down quarks. The sum is 0. Thus, the neutron's neutrality is not an absence of charge, but a balance of charges, hidden within its interior. The quarks themselves are charged, but their combination cancels perfectly, producing a particle that to the outside world appears neutral. This neutrality is no trivial accident. It is a vital property that allows neutrons to play their role in nuclear stability. If neutrons carried any net charge, however small, the balance of forces in the nucleus would be disrupted. Nuclei might not form beyond hydrogen, and the periodic table as we know it would collapse. The very existence of heavier elements, carbon, oxygen, iron, depends on the neutron's exact neutrality. In this sense, the neutron is not merely a companion to the proton, but the enabler of complexity. It is because neutrons exist, and because they carry no charge, that the universe has diversity, structure, and life. The neutron's neutrality also gives it unique powers. Unlike charged particles, neutrons can pass through matter with relative ease. They do not interact with electric fields, so they are not deflected by atomic electrons or protons. This makes them invaluable in probing the interior of materials. In modern science, neutron scattering is used to investigate the structure of crystals, proteins, and even magnetic materials. Their neutrality allows them to slip between the barriers that block charged particles, revealing secrets hidden deep inside matter. This same property makes neutrons dangerous in uncontrolled circumstances, as in nuclear reactors or weapons. Neutrons can travel into surrounding material, striking nuclei and triggering further reactions. Their lack of charge gives them a reach that charged particles cannot match, making them central to both the promise and peril of nuclear science. But the neutron is not stable forever. Outside the nucleus, free neutrons decay with a half-life of about 15 minutes, transforming into a proton, an electron, and an antineutrino. This decay, known as beta decay, is one of the fundamental processes of particle physics. It reveals the neutron's hidden duality. Though it appears neutral, it is always on the edge of transformation. Its internal quark structure capable of shifting through the weak nuclear force. One of its down quarks converts into an up quark, turning the neutron into a proton and releasing the accompanying particles to conserve energy and momentum. This delicate instability is crucial to the universe. In the early moments after the Big Bang, free neutrons decayed or were bound into nuclei, shaping the abundance of hydrogen and helium that seeded the cosmos. Without neutron decay, the balance of elements would be vastly different, and stars and galaxies would not have formed as they did. The neutron's hidden role in the nucleus extends to the landscape of isotopes. Elements are defined by the number of protons in their nuclei, but their isotopes differ by the number of neutrons. Carbon, for instance, has 6 protons, but it can exist as carbon-12, carbon-13, or carbon-14, depending on how many neutrons it contains. These isotopes have nearly identical chemistry because their electron structures are the same, but their stability differs dramatically. Carbon-12 and carbon-13 are stable, while carbon-14 is unstable, decaying over thousands of years and providing the basis for radiocarbon dating. This reliance on neutrons demonstrates how profoundly they shape the world. Without them, isotopes would not exist, nuclear reactions would not power stars, and the tools of archaeology and geology would lack their most precise clocks. The hidden role of neutrons also appears in the nuclear shell model, an analogy to the electron shells around nuclei. Just as electrons occupy discrete energy levels, so too do protons and neutrons within the nucleus. Stability emerges when certain magic numbers of protons or neutrons fill these shells, producing especially stable nuclei. These magic numbers, 2, 8, 20, 28, 50, 82, 126, reveal that neutrons are not passive participants, but active players in the quantum choreography of the nucleus. A nucleus with the right number of neutrons achieves an extraordinary degree of stability, explaining why some elements are more common in nature than others. The neutron, invisible to our senses, orchestrates this balance, determining the rhythm of nuclear existence. And yet, the neutron remains an enigma. Why should a particle exist that is so similar to the proton in mass, but entirely different in charge? Why should it decay outside the nucleus, but persist indefinitely inside? Why should it possess a magnetic moment, hinting at its internal structure, even though it is electrically neutral? These questions remind us that the neutron, though discovered nearly a century ago, still guards secrets that modern physics struggles to unlock. It is a reminder that even the most ordinary building blocks of matter can harbor mysteries as profound as the cosmos itself. The neutrality of the neutron, then, is not a mere absence but a profound presence. It is the quiet balancing act that permits atoms to exist, isotopes to form, stars to burn, and life to endure. In the great drama of the atomic world, the proton and electron take the leading roles, their charges visible and dramatic. But it is the neutron, silent and unseen, that holds the stage together. Without it, the story would collapse before it could even begin. To understand the deeper importance of the neutron, one must step back and realize that neutrality is not an absence, but a delicate balance of competing forces. When James Chadwick announced his discovery in 1932, many physicists immediately recognized its elegance, because the neutron was the answer to so many puzzles at once. It explained the missing mass in atomic nuclei. It explained how protons could coexist without tearing the nucleus apart, and it explained why isotopes of the same element had different masses. But the implications went far beyond filling gaps in atomic bookkeeping. The neutron opened the door to a new understanding of nuclear energy and the forces that sculpted the universe. The neutrality of the neutron allows it to perform feats that neither protons nor electrons can achieve. Protons, with their positive charge, cannot easily penetrate a nucleus because they are repelled by the positive charge already inside. Electrons, being so light, do not influence nuclei in the same way and are largely confined to their orbits. But neutrons, unaffected by electric charge, can slip past the electromagnetic defenses of a nucleus and enter directly. This property is the reason nuclear reactors work. In reactors, neutrons collide with uranium or plutonium nuclei, causing them to split in fission reactions. Each fission event releases more neutrons, which in turn strike other nuclei, sustaining a chain reaction. Without the neutron's neutrality, this process would be impossible. The neutron is the invisible spark that drives the immense energy released in both nuclear power and nuclear weapons. The irony is that this neutrality, which makes neutrons such potent agents of nuclear change, also makes them incredibly difficult to detect and control. Unlike charged particles, they cannot be guided by electric or magnetic fields. Early nuclear physicists faced immense challenges in building detectors sensitive enough to register the passage of a neutron. Instead of tracking charge, they had to observe the neutron's secondary effects, collisions with protons, for instance, that would produce recoil detectable in scintillators or cloud chambers. This difficulty underscores the neutron's nature: silent, elusive, but immensely powerful in its consequences. Beyond reactors and weapons, the role of neutrons stretches into the cosmos itself. Consider the life of stars. In the dense cores of stars, protons fuse to form helium, releasing energy that sustains stellar light. But as stars evolve, especially massive ones, fusion reactions involving neutrons become increasingly important. Neutrons are the gateway to building heavier elements. Through processes known as the S process, slow neutron capture, and the R process, rapid neutron capture, neutrons are absorbed by atomic nuclei, gradually or explosively building up the periodic table beyond iron. The gold in rings, the iodine in human bodies, the uranium deep in the earth. All of these exist because neutrons, in stellar furnaces and cataclysmic supernova, quietly performed their role as builders of elements. Without neutrons, the universe would have stopped at helium, and the richness of chemistry would never have come to be. The same neutrality that makes neutrons ideal cosmic architects also makes them the building blocks of one of the strangest states of matter known to science, the neutron star. When a massive star explodes in a supernova, its core collapses under immense gravity. Protons and electrons are crushed together, producing a sea of neutrons. The result is a neutron star, an object so dense that a teaspoon of its matter weighs as much as a mountain. Here, the neutron reveals its ultimate strength. Stripped of their individuality, packed tighter than atoms allow, neutrons form a degenerate state of matter balanced by quantum forces. The neutrality of the neutron permits this packing. If each neutron carried charge, electrostatic repulsion would prevent such extreme densities. Neutron stars, with their powerful gravity and magnetic fields, are among the most exotic and awe-inspiring consequences of neutrality in the universe. Yet the neutron is not immortal. Outside the nucleus, as mentioned earlier, it decays into a proton, electron, and antineutrino. This decay is not a flaw but a vital feature. In the early universe, just minutes after the Big Bang, the balance between neutrons and protons set the stage for primordial nucleosynthesis. Free neutrons decayed, but enough were captured into nuclei to form helium and traces of other light elements. Had neutrons been perfectly stable, or had their lifetime been dramatically different, the ratios of hydrogen to helium would be altered, with consequences that would ripple into the formation of galaxies, stars, and planets. The neutron's finite half, life, seemingly arbitrary, is in fact a cosmic parameter tuned to allow the universe as we know it to exist. This fragility is also a tool. Physicists study free neutron decay to probe the weak nuclear force, one of the four fundamental forces of nature. Each neutron decay is a laboratory for testing the standard model of particle physics, and any deviation from expected behavior could hint at new physics beyond our current understanding. Indeed, the precise lifetime of the neutron remains a subject of controversy. Different experimental methods produce slightly different values, and the discrepancy has sparked debate about whether unknown particles or forces might be involved. Thus, the humble neutron, neutral and unassuming, could hold keys to unlocking mysteries at the frontiers of physics. On Earth, neutrons also shape our world in subtler ways. Cosmic rays striking the atmosphere produce showers of neutrons that cascade down to the surface, influencing everything from natural background radiation to the mutation rates of living organisms. Some scientists even speculate that the flow of neutrons from cosmic rays has played a role in biological evolution by driving genetic change. In a more practical sense, neutrons power technologies that permeate modern life. Nuclear reactors generate electricity for cities, while neutron activation analysis is used to detect trace elements in forensic science, archaeology, and industry. Neutron therapy has been explored in medicine for treating cancers. Their neutrality makes them penetrating, allowing them to reach deep into tissues or materials where other probes fail. The neutron's neutrality, however, hides an important subtlety. It is not perfectly featureless. Though its overall charge is zero, its internal quarks give it a distribution of positive and negative regions, a structure that manifests in its magnetic moment. This means that while neutrons do not respond to electric fields in the way charged particles do, they still interact with magnetic fields. This property is exploited in neutron scattering experiments to study magnetism in materials. It also hints that the neutron's neutrality is more complex than a simple absence. It is a composite balance, a harmony of opposites contained within. At the deepest level, one must ask why such a particle exists at all. Why should nature produce a partner to the proton with nearly identical mass but neutral charge? Why should quarks arrange themselves into this delicate cancellation? The answer is not fully known. Symmetry arguments in particle physics suggest that the existence of the neutron is tied to the fundamental organization of matter. Protons and neutrons, collectively known as nucleons, form an isospin doublet, two manifestations of the same underlying field. This symmetry ensures that both exist, one charged and one neutral, to allow the diversity of atomic nuclei. It may seem arbitrary that neutrons turned out neutral rather than positively or negatively charged, but this arrangement creates the balance required for stable atoms and the variety of matter. If the rules had been different, if neutrons had even a slight charge, the story of the cosmos would collapse. In many ways, the neutron embodies the idea that what is unseen can be most essential. For centuries, science advanced by focusing on the visible and the measurable, on sparks of electricity, on beams of light, on planets moving across the sky. The neutron challenged that world, by insisting that neutrality, absence of charge, could be as fundamental as presence. It forced physicists to look beyond what detectors could easily measure and to recognize that the most powerful forces may act in silence. The neutron does not light up with sparks, it does not bend in magnetic coils, it does not leave tracks like electrons. And yet, without it, the universe falls apart. From the stability of nuclei to the alchemy of stars, from the quiet decay of free particles to the crushing weight of neutron stars, the neutron plays a role far greater than its modest name suggests. It is the mediator, the stabilizer, the architect, and the destroyer. Its neutrality is not a deficiency, but its greatest gift, allowing it to move invisibly through matter, to bind nuclei, to build worlds, and to seed life. If the electron's negative charge and the proton's positive charge are the opposing notes of nature's symphony, the neutron is the silence between them, the pause that gives meaning to the sound. The secret of atomic charge is thus incomplete without appreciating the neutron. Electrons and protons provide the visible dance of attraction and repulsion, the charges we can measure and manipulate. But the neutron, in its neutrality, reminds us that balance is not only about opposites, but about harmony. The neutrality of the neutron is the hidden foundation upon which the universe builds its complexity. To ask why the neutron is neutral is to confront one of the deepest questions in physics. Why does the